Okay, brief rundown of graph trapezoids and their labeling. Graph trapezoid starts with 2 points. And from those 2 points, we create the rest of it. Well, it starts with 2 points and an axis, which I'll refer to as the horizontal axis. It doesn't actually have to be horizontal. It could be tilted at any angle. But we project each of the points to the axis. And the projection has to make a right angle with the axis. So these yellow lines represent the projections. And we call the length of this line graph altitude 1 and graph altitude 2. I didn't put the graph adjective in there, but I'll kind of abbreviate it in the longer version. I make this real clear, but okay. And then we do the approximating segment, the line segment from one point to the next. We call that the approximating segment, the slope segment. So we start with 2 points in the graph, do our projection lines to the axis, and sketch our approximating segment. And there we have a trapezoid. Not only a trapezoid, but a trapezoid in which the 2 parallel sides make a right angle with a third side. And then there's a fourth side that is generally parallel to either of the others, any of the others. Okay, we label the trapezoid. Okay, first of all, we label the projection lines with their lengths. We call these the graph altitudes. So we're going to put a number here for the length, a number here for the length. No symbol around the number, just right next to the projection line itself. Then we label the interval of the axis with its width. Okay, so whatever the width is, whatever the distance in the horizontal direction or the direction of the axis from this point to this point is going to be the width. And the approximating segment we're going to label with its slope. Finally, the inside of the trapezoid is going to be labeled with its area. Now, to indicate numbers that mean slope rather than a length, we can put a box around it. And area, again, to distinguish from lengths and other possible dimensions, with a circle around it. To illustrate, we calculated slope and area, and you should do this yourself without looking at how I've calculated things. With a graph altitude of 18 on this side, a graph altitude of 24 on this side, and a width of 5. What therefore is the slope of the approximating segment or the slope segment, and what is the area of that trapezoid? Now, I caution you, I don't want to see the area of that trapezoid calculated by using the formula for the area of a trapezoid. The area of a trapezoid is easily found by reconstructing the trapezoid into a rectangle, or by using some sort of common sense, which is pretty much equivalent. So hopefully you can do that without having to resort to any formulas. And I'm not necessarily referring to the formula for a slope or the formula for the area of a rectangle. You should know those well enough that they don't really present themselves in your mind as formulas. You should know what a slope is. You should know what the area of a rectangle is, and a very deep manner. If you don't, well, we'll try to make it a little deeper as we go on. But you should calculate those things. Now, hopefully you've not only done these calculations for yourself, but you've gotten a slope of 1.2 and an area of 105. And I hope I'm right as I go through this. We'll see if I maybe made a mistake somewhere, but I don't think so. Okay, so to calculate the slope, we're going to do a run of 5 and a rise of 6. The run being parallel to our axis, the rise being perpendicular to our axis, and the run going from this point to this point, parallel, and then the rise again from this point to this point, but in the direction perpendicular to the axis. So we have a run of a run of 5, a rise from 18 to 24, which is 6. We don't need formulas to calculate those if we've got these numbers. Okay, now I talked about how you calculate the area by reconstructing a trapezoid into a rectangle. It's easy to reconstruct a trapezoid into a rectangle. We take the midpoint of the approximating segment and we sketch a line parallel to the axis. This divides the trapezoid into it divides the trapezoid into a lower part and gives us a small triangle above that we can cut out of the trapezoid, invert, and paste here to construct a rectangle. Now you should be able to go through the entire geometric argument that proves that dividing this at the midpoint, first of all, gives you a triangle here, and when pasted here, that triangle completes a rectangle. The width of that rectangle, of course, is the width of your trapezoid. The average altitude, what I'll refer to as the average altitude, you can think of that as the length of the rectangle, but when we're talking about graphs, we're going to use altitude for things that go in this direction. The average altitude is going to be just the average of the two altitudes. And of course, you should be able to prove that as well using the geometry and using other definitions. But we can then calculate the average altitude or the length of this rectangle as altitude 1 plus altitude 2 divided by 2. In the case of this trapezoid, of course, we don't really need to add these two and divide by 2. We can see very easily that 21 is halfway between 18 and 24. At least I hope everybody can see that very easily. If you reach for your calculator to calculate the average of these two numbers, you're not invoking your brain, and you're bypassing it and allowing the calculator to do your thinking for you. That's fine if you have really horrible numbers here, 5,628 and 14,792. By all means, reach for your calculator, although you should understand that the average of those two is probably somewhere between 9,000 and 10,000. Okay? Okay, in any case, you calculate the average altitude, you multiply it by the width, and you have your area. So we've done that here. Average altitude is 21. The width is 5. We've known that all along. So the area is 21 times 5, or 105. And we put that in the middle of the trapezoid with a circle around it, just as we put the slope, 1.2, in a box above the approximating or slope segment. And of course, the slope was calculated by dividing the rise 6 by the run 5 to get 1.2.